Okay, so we will be recording this part of the session. If anybody has any objections with the recording, please say so now. Okay, so we had talked in the previous session, we were working on, or we were discussing electrical fields of objects with a defined geometry that have a continuous charge in them. And we were talking about three examples: charged line, charged ring, and charged disk. And we had seen what the expression, the mathematical expression was for the electrical field at a certain distance of a line charge that has a certain length and a certain charge distribution. And we had seen two problems where we found the electrical field by a 1 meter line that has a charge of 1 microcoulomb at a distance of 1 meter perpendicular from the center of the line, and also the electrical force between the line and the charge. And so we had done this where we had identified the different elements and done the calculations according to the expression. Now we're going to talk about on the electrical field of a ring. And so the electrical field of a ring is given by this expression. I'm sorry. The electrical field of a ring is given by this expression here. And how do we obtain this expression? Well, basically we obtain a differential here of the electrical field at a certain distance from the center. And then we integrate this along the whole circumference, and we obtain this. This integral, to get from this to this, is bonus number 2 that you can turn in today before midnight. Same dynamic, just do the integral with the complete procedure and explanation, do it by hand, take some screenshots, and turn in a PDF of this via email, okay? And that'll count as a bonus. And so now let's apply this expression. So it says, find the electrical field generated by a 1 centimeter radius ring with a uniform charge of +2 microcoulombs at a distance of 1 meter perpendicular from the center of the ring. So similar to how we did it in the previous problem, we're going to identify the different elements that we have and try to relate them. So first off, for this specific problem, the radius of the ring is 1 centimeter. It's 1 centimeter, which would be 0.01 meters. That would be the radius, okay, which is this element here. Let's use different colors here so we can mark them. So the radius, which is this element here, they're calling it R prime in this slide. They're calling it R prime, just so I'm not confused because there's a 2 there. So this R prime is this one here, and it is 0.1 meters. Okay. The other information we have is that there is a uniform charge that is located at 1 meter from the center of the ring perpendicular to the ring. So we have a 1 meter distance here. One meter distance from the center. And this 1 meter that we have here, this is Z, which is the distance that we have from the center. Z. And it's basically this Z that we have here. And it is 1 meter, okay? What else do we need to be able to do the calculations? Well, we already know K, right? We already know K. K is the the electrical constant. We know that by heart. This is 9 times 10 to the 9. Okay. And what's the last thing we need here to be able to do the calculations?
Lambda.
Lambda, perfect. Thank you, Lucia. I'm going to change the color of this just because I'm a little OCD here. I think we used lambda in the last one. Lambda was purple, and I just like my colors to be congruent. So I'm going to use pink for Z.
We don't need any inequality.
Okay, and this is Z. And so we need lambda. And what is lambda? But lambda is the linear charge density, which is basically the amount of charge that we have around the density of charge in the ring, the linear charge density. So what would be the linear charge density in this case? How do we calculate that?
The Q over L or what?
It would be Q over L. Okay, you answered exactly like my daughter does when I ask her something. It's like, what is this? Well, is it this or what? Yeah, so it's Q divided by L. But in this case, L is the whole linear space that we have here, which would be the perimeter of the ring. Okay, so Q is equal to Q in this case is 2 microcolumns. I'm gonna write this somewhere else. In a moment, just to have a little bit more space here. So lambda, I'm gonna bring it over here. Lambda, like Carmina said, is gonna be Q. Zoom windows are really annoying. It's gonna be Q divided by L. But in this case, L would be the whole distance of the whole length of the ring, which would be that perimeter. So Q is 2 microcolumns, which is 2 times 2 times 10 to the minus 6 columns. And how would we calculate the perimeter? What would be the perimeter of a circle? How do we calculate that?
First of all, how do you get the 2, Professor?
This 2, it's
the problem.
The problem says that the ring has a uniform electrical charge of 2 microcolumns of 2 microcolumns, which would be 2 times 10 to the minus 6. So how do we calculate the perimeter of a ring or a perimeter of a circle?
The circumference.
The circumference,
Oh, it's 2 pi radius.
correct. So it would be 2 times pi times the radius, which in this case would be 1 centimeter, which would be 0.01. Okay. And this is a value that we're going to calculate. Okay, so now that we have all of these, okay, we can calculate the electrical field, okay, which is what we are looking for. So what I want right now is that I'm going to ask House Clerks of Maxwell, please, to do the calculation of the electrical field and give us the value. And I want House, let's see, House Pivana to validate. So you also do the calculation and validate the value. Okay, so we've got all of the values here. Let's drop them into the expression and find the electrical field. So please do that. When you're ready, give me the value.
I couldn't hear. Could you repeat what you said, please?
Yes, I'm asking, we've identified all of the values that we need. So I'm asking House Clerks of Maxwell to do the calculations. Please find the electrical field. And I'm asking House Pivana to please validate. So both houses are going to do the calculations. I want Clerks of Maxwell to tell me the electrical field is this, and I need House Pivana to tell me, yes, we verified the calculation and it's correct, or maybe we got something different, and to get to the final value. Okay. So
Okay.
please,
Thank you.
yeah. Okay. So please do the calculations, Clerks of Maxwell. Let me know when you've got the result.
Professor,
Yes,
at the top, it's 2 times 10 minus,
minus
what was it?
6. Minus 6.
Minus 6. Okay, thank you.
The R is the point 0.01 meters, right?
The R prime. The R prime. And I'm just going to clean this up a little bit. While you guys do that, let me. This slide has less space than the other one that we were using. So I'm going to say lambda. Equals Q. Divided by L. Q is 2 times 10 to the minus 6 columns. And we're going to have 2 pi multiplied by R. Zero point zero one. Okay, as soon as you guys have the value, please let me know, and so we can corroborate.
Professor, I think we already got our calculations.
Okay,
We
let's
have
see.
17,997.3.
17,000.
997.3.
So I'm gonna actually round it up because we're
Okay.
doing so it's approximately, we're talking about 18,000. Rounded up 18,000 Newton's columns. Okay.
Professor,
Mhm.
so we also made our calculations and we were unsure because there are a lot of numbers, but yeah, we actually got same value, 17997.
Okay, perfect, perfect. So roughly 18,000, roughly 18,000 Newton's column. Okay. Okay, good. And so now let's assume, so thank you very much, you guys, both houses. So now let's assume that we place a negative charge here. We place this is for problem 2. Now let's assume that we place a negative charge here. And so if the ring is positive, then we are going to have a force that's going to be going downwards here. And this, in problem number 2, we want to find what force would be exerted on that charge. And that charge is -3 microcoulombs. So we know that the force exerted on the charge is going to be equal to the electrical field that we just found multiplied by the charge. Okay. Multiplied by the charge. Okay. And can somebody let's see how's delta sigma, please. Let's do this calculation. Sorry about that. This is going to be recorded. Somebody's knocking at the door apparently. So how's delta sigma, please help us out with that calculation. It's basically E, which is the one we just found, multiplied by the 3 microcoulomb charge that we have there. So
Professor,
yes.
10,000 or
Yes, could you repeat that, Marisa? It kind of.
do we need to use 18 or the exact number we got?
We can use you can use the 18,000. We're going to do an approximation. So that's actually the multiplication will be easier.
I got negative 0.054.
0.054. 0.054.
Yes.
Okay, and these will be these would be newtons. The negative only means that would mean, if we were to interpret it with the sign, it would mean that the charge is going downwards. Oh, I'm sorry, the force is going downwards. Okay. Okay, so this would be the charge for the disk. Okay. And so, oh, by the way, I apologize. I made a mistake with the bonus. Actually, I wrote down something wrong here. I said that the bonus would be going from this differential to this expression here. And actually, no, because it's the same expression. The bonus, there's actually two bonuses, not three. The first one is the one you guys did with the integral. This one doesn't have an integral. Actually, it's just directly the same contributions. It's exactly the same case as the line that we had, but now the line is in a circle. The integral is going to be the next one, which is going to be the disk. Okay. Okay. So let me move this up here, so I can take a screenshot before we go on to the next one and last one. Okay. So give me a moment. There we go.
Professor?
Okay, here we go. Yes, go ahead.
And is the disk integration bonus for today or tomorrow?
Let's have that one for tomorrow.
Okay.
Okay. Yeah, you can let's have one more day. Okay. Okay. Okie dokie. So we're going to move on. I just took a screenshot of this. We're going to move on to the next one then. So I'm going to clear this in 3, 2, 1. Boom. Okay. And before we go to break, let's set up this. Now we have a disk of charge. Now it's a disk of charge. And the disk of charge, the difference here is that now we have a planar surface that has a certain uniform charge in it. And this is the integral we're talking about, the integral that basically we take the disk expression and then we integrate it along the radius, and this is how we get the expression for this is how we get the expression for the electrical field, which is the one we're interested in. Now, in the first scenario or problem we're talking about, we want to find the electrical field generated by a 1 centimeter radius disk with a uniform charge of 3 microcoulombs at a distance of 1 meter perpendicular from the center of the ring, or the disk, rather. And so let's set this up before we go to break, and then we'll just do the calculations. Give me a moment. There we go. I need to correct something here. We're talking about a disk. Okay. And so what's the information that we have here? Well, the information we have is that the disk has a radius of 1 meter. Okay, so the radius of the disk is, I'm sorry, 1 centimeter. It's 0.0 0.01 meters. This would be the value of R, which is the radius of the disk. And the point that we're analyzing for this problem is also located at 1 meter distance from the center. And this 1 meter would be, in this case, Z, which is the distance that we're trying to analyze. And this would be this Z here. We already know K, which is the electrical constant that we always work with. K is equal to 9 times 10 to the 9. And the last thing that we need to find here is the sigma. Now, what does sigma represent? Again, it represents the density. The density is how much charge we have in the object that we're analyzing. So in this case, the density isn't going to be a linear density. It's going to be a superficial density because we have a surface. So the superficial density is going to be Q. The superficial density is going to be equal to Q, which is the total charge, divided by the area. And in this case, Q, we have the charge is 3 microcoulombs, which is 3 times 10 to the 6. Coulombs. And the area in this case is going to be this, or the surface area is going to be that of the disk. And in this case, that would be pi multiplied by the square of the radius. And in this case, the radius would be 0.01 meters. And we want to find the electrical field here, this electrical field. Okay, I want, please, let's see who's missing. Pichitas, oh, I forgot, you didn't, it wasn't.
Yes, I have a
Pichitas.
question, Professor.
Yes, go ahead.
So the area is pi times radius squared, right?
Yes, it's squared. I forgot to put the square here.
Okay.
Yep. Good catch there.
Okay, thank you.
Squared, good catch. Squared. Pi times the radius squared, correct. So I want Pichita's Revenge House to do the calculation for E, please. Okay. And what house am I? Oh, and I want Electric Bakers, please, to do the validation. Okay. We're going to do that when we come back from break. Okay, so we're going to take a 10-minute break and come back with this. Okay, so we are going to do the calculations for this problem. Just a note, just because all this is being recorded, I again, sometimes the fuzzy brain gets me. And remember that you guys, I need you guys to be paying attention and correct me, as Omar did a few moments ago when I missed the square in the radius in the formula here. Just remember that when we're talking about microcolumns, remember that it's to the -6, okay? Don't remember if I put the minus when I wrote it down, but remember it's a -6, okay?
Yeah, I asked Omar actually because I also saw the 6 and I thought it was -6.
Yeah, it's -6. So remember that the micros are always going to be -6. Okay, so Pichita's Revenge, could you please give us the value you got? Or when you have the value, please let me know. And Electric Bakers, please validate, verify the calculations.
Professor, we got 27,000.
27,000, probably rounded up.
Yeah.
Also? Okay, 27,000. Now, notice that remember, this is important. Notice that we're getting very large values for the electric field. That's normal. We're getting very large values. But remember that an electrical field is newtons per coulomb. So that is the effect per coulomb. So these are newtons per coulomb. House Electric Bakers, just to validate, did we get something similar?
Yes.
Okay, I'm going to trust you guys. Okay, good. Now, similar to the others. Now let's assume that we've got a negative charge here. We've got a negative charge here, that negative charge is for microcolumns. And so if we put a negative charge in that electrical field, we're going to get a force that is going to attract the charge to the disk. And this force, similar to the other problems we've seen, is equal to the electrical field that the disk is generating multiplied by the charge. And so please, let's see, let's have house, let's go back to Clerks of Maxwell. Clerks of Maxwell, what would be the force that's being exerted on that charge based on the electrical field that we just calculated and assuming that the charge is for microcolumns? Let's have Clerks of Maxwell, please. Okay.
I'm doing the calculations.
Mm-hmm. Perfect. Okay, so it's actually it's 27,000 multiplied by 4 times 10 to the minus 6.
Yes, I already have it. It's
Okay, perfect.
0.108.
0.108, and we're talking about newtons. Okay,
Yes.
so that would be the force that's exerted in that charge. Now, what could be variations of this? Well, maybe the charge of the disk is negative. What would be the only difference with the electrical field if the charge of the disk were negative? Instead of the electrical field going outwards, it would be going inwards. What if the test charge is of the same sign? Well, the only differences would be that the force would be a repulsion force, but the calculations still apply. Okay. Good. I'm going to, so this recording is going to be up in Blackboard today, along with the complete PowerPoint with the solving of the problem solved.